In mathematics, a coloring problem is answering the question of whether or not a completely arbitrary map of very peculiar shaped countries can all be colored with n colors such that no two bordering countries share the same color. It's rather obvious that if n is 1, 2, or 3, that's not enough. And by the 1800s, it was mathematically proven that 5 could always do it. But no one was sure about 4. Some people still aren't. In 1976, a computer-assisted proof was presented, meaning that the problem was solved simply by brute force checking all of the possible types of maps that could exist, and failing to find even one where 4 colors wasn't enough. Accepting of this proof requires a trust in the program that did the checking, a belief that it has no bugs, and that the hardware it ran on had no known defects, or more importantly, no unknown defects, nor was it hit by a cosmic ray during the operations. It was simply infeasible for one person to check all those results. And for a time, the field of mathematics was not in consensus on this proof. This is Data Skeptic Consensus, and the 16th installment in our series about how multi-agent systems achieve collective decision-making. Today on the show, I share a few thoughts about the recent CASP 14 protein folding competition and the belle of the ball, AlphaFold 2, whose impressive result seems poised to be a revolutionary breakthrough for biology. So what is AlphaFold? It's a software system relying on many of the techniques we discuss on Data Skeptic, deep learning and that sort of thing, as well as many biological techniques we don't discuss on this show. It is a truly interdisciplinary breakthrough, which is able to predict the 3D structures of proteins based on the sequence of amino acids that compose them. Proteins consist of 20 different amino acids, and the structure of that protein, which is the hard thing to predict, is sadly also the most interesting thing. The protein's structure determines its biological function. Proteins, as you can imagine, are quite small. That's why we can't just look at them to see what their shapes are, or at least not look at them directly. This is something that bothered me when I was younger and I was learning about things like the atom, and hearing that the electron was never exactly in one place, that it existed as a potential cloud, or really just a probability distribution over where it might be. Maybe that worked out on paper, but I wanted to know, what if I could zoom in, or shrink myself down, or get a really high-powered microscope? What would it really look like if I could get down there and see it? And I eventually learned that was a nonsense question. It's like asking, what does the sun taste like? We're talking about atomic scales. The errors that AlphaFold made were on the nanometer scale. As far as seeing, at least with my eyes, that's going to require photons, and if something is skinnier than the period of the photon, well then there's no way to really see it, but it's there. So scientists have developed many ways of seeing, or I'm just going to start saying observing proteins. X-ray crystallography is a diffraction technique. Nuclear magnetic resonance takes advantage of properties we know about oscillating magnetic fields. And cryogenic electron microscopy is a third technique whose mechanism I can't well articulate. But these have been the major techniques that scientists use to experimentally determine the structure of proteins. So why do we need AlphaFold at all if we have 3 techniques? All of these are insanely expensive, require a tremendous amount of training, and are in some ways error-prone. Although, no disrespect to the operators of these machines that work in those labs. I don't know where this figure came from. I couldn't find an original source, but I found a lot of popular press quoting the number $200,000 as the cost of establishing one protein shape through some of these methods. So you've got the choice between, a down payment on a house or knowing the shape of a protein. Also commonly cited is the opportunity for this to advance drug discovery. My understanding of this is that in many cases, drugs are designed to kind of fill in the blanks or do something that a protein isn't doing, to mimic its shape and therefore mimic its mechanism. I was trying to come up with a programming analogy here, and maybe saying that the amino acids were the binary code and the proteins were the assembly language. There's a structure to them, but very archaic and hard to read by human eyes. I prefer to read it in the original C myself. I'm not a biologist, so I'm not going to speculate on this, but it is quite clear this is a fundamental and major breakthrough. I don't know if my analogy is fair, but I would maybe compare this to a breakthrough in quantum computing. That doesn't change everything about computing. Overnight or soon thereafter, we'd see improvements in search thanks to Grover's algorithm, and in integer factorization thanks to Shor's algorithm. But I lack the creativity to appreciate the full breadth of what it might mean for a practical quantum computer to exist. And I also lack the background and creativity and breadth to understand what AlphaFold is going to do for us in the future. But I'm very eager to watch this story unfold, as I'm sure it will. Thank you to my friends at Brilliant for sponsoring this episode of Data Skeptic. You guys know these longtime supporters, and as we get into the holiday season, this is a great last-minute gift. Think about the person in your life who'd love to get access to 60-plus interactive courses. Maybe just buy it for yourself. Head over to brilliant.org/dataskeptic to see what they've got available. I wish Brilliant had been around when I was starting in algebra and trigonometry and geometry and calculus and all those fundamental mathematical subjects. I would have had such an easier time with the material. Of course, these days their quantum computing and group theory courses are catching my eye more than the mathematical fundamentals. There's something for everyone at Brilliant. Their courses are award-winning and well-deserving, I would say, taught by teachers, researchers, and professionals from MIT, Caltech, Duke, Microsoft, Google, and many more. Whether you're looking to learn, stay sharp, or just exercise your curiosity, head over to brilliant.org/dataskeptic. What I can comment a bit more on is the implementation of it, how prior work with DeepMind has contributed to this, and maybe what we take back in the machine learning community and apply elsewhere. So why is AlphaFold in the news? Well, it's because of the wrap-up of the recent CASP 14 competition. CASP is an acronym, or almost an acronym, for Critical Assessment of Structured Protein Prediction. 14th biannual running of this event. In 1994, this got together to really establish the state-of-the-art in what protein folding could be done automatically. Many people quite fairly are comparing this to ImageNet, and its impact as the benchmark in computer vision. And much like ImageNet, there seems to be a consensus in the appropriate protein folding communities that this is now a solved problem. The score they were looking for is around 90, and AlphaFold is right in that neighborhood. But what is that 90? Let's talk about the actual metrics. While data scientists and machine learning people might be most familiar with things like accuracy and F1 score, the CASP competition's metric is something called GDT, the Global Distance Test. And it's, for most intents and purposes, an accuracy measurement. It compares the predicted protein shape to the actual experimentally known result. There's some great graphics online where they've rendered a 3D model, and green is the experimental shape, and blue is AlphaFold's prediction. I may have swapped those, but in any event, you can see these effectively isomorphic structures overlapping each other. In fact, from doing a little research here, it seems they're calling into question whether or not those differences are even real. Those could be artifacts of the data, or those three processes by which the ground truth was eventually collected. Remember, we can't see these proteins. We're verifying an algorithmic prediction against the measurements of highly advanced, high-precision equipment. Yet, nonetheless, equipment trying to measure something very, very small, and I presume somewhat fragile when put under the conditions for proper observation. DeepMind's entry AlphaFold also participated in 2 years ago's competition, CASP 13, and with much less fanfare, they took first place in that one as well. In CASP 13, AlphaFold took first place, winning out over second place by just 6 points. In contrast, although many of AlphaFold's techniques have been embraced by other competitors in the space, AlphaFold converted that 6-point lead into a 25-point lead for first place this time. Certainly more important than that, it places this algorithm, or this process, into the range of what people considered solved. While it might still be considered a proof of concept of sorts, it won't be long before there are research, commercial, and industrial applications of this. Congratulations to the AlphaFold 2 team, as well as Baker Experimental, FigRG, Zhang, Tful, Human Multicom, and so many of the other participating teams that did exceptionally good work as well. So what does AlphaFold do? Well, I'll talk about it from sort of a programmer's perspective first. There's an encoding process. If you look at their GitHub, you can see that initial amino acid sequence, which is often written as just letters, they do a one-hot encoding of that, producing a large but finite vector of initial results. There's a series of feature engineering processes that they go through after that. Now, interestingly, many of those feature engineering tools they built don't seem to have been used in the final model. They check them as not needed. However, it isn't just the encoding. It's a few other auxiliary features that go in as well. It'll come as no surprise that transformers and attention play a featured role in the success of this model. I'm reminded of how these mechanisms were the key breakthrough in natural language processing in models like BERT. They teach the model what to pay attention to, and to some extent, what recent things to remember. Let's do a for instance. For instance, I was telling you a story about some crazy weekend I had, and to kick it off, I said something like, me and some buddies drove up to Vegas for a 4-day weekend. Now, I may never again mention that the setting for the story takes place in Las Vegas, Nevada, but that is a bit of information that you as a listener will likely carry through. Everything I say throughout the rest of this hypothetical story, which might involve gambling and who knows what else, takes place in the context of the city I only mentioned once. But what context do we have in protein folding? Well, for the average person, me included, none whatsoever. But have you heard about those stories? And I need to verify this, but I'm going to repeat it anyways because it sounds nice. If you put chess pieces randomly on a chessboard and flash a 1-second image to people, they do a baseline, not very good, but somewhat good job of rebuilding that actual chessboard, putting the pieces that they saw into the positions they saw them in. And if you randomly toss random pieces on a chessboard, both chess amateurs, or people that don't even know the game very well, and grandmasters alike have about the same recall. In other words, being good at chess, or I guess not even just good, but experienced at it, that doesn't give you an advantage in recalling a random chessboard. But if you change up this experiment and you show chessboards taken from actual games, the non-chess players perform about the same. But the chess players, the experienced players, their recall goes significantly up. Why? Because with a chess player's eyes, they don't just see the individual pieces anymore. They see the strategy. Black is doing the Queen's Gambit, and white is playing the Kasparov curveball. I made that one up. The massively parallel deep neural network, and I mean actual neural network, that's in the brains of those chess players, it's been trained to efficiently recognize certain important features of the chessboard. Those features aren't present in random configurations. They're a product or an artifact, depending on how you want to look at it, of actual gameplay. And this is more or less what attention brings to the table for AlphaFold as well. As these tiny sequences of amino acids begin to fold, who's doing the folding? Well, it's nature. They're following the laws of nature very mechanically. Certain aspects of that protein might be water-phobic or attractive to other parts of it. It's very easy to be the referee of a one-dimensional tug-of-war game, maybe even 2 dimensions. But in 3 dimensions, complex interactions can emerge, and it might just so happen that as a protein is folding, certain attractive or repulsive subregions of it pass each other like ships in the night, and all of these contributions contribute to making this a hard problem. Thanks to this week's sponsor, BetterHelp. BetterHelp is an online professional counseling platform. They will assess your needs and match you with your own licensed professional counselor. You can start communicating in under 24 hours. It's safe, private, and convenient. It's exciting to think what technologies like AlphaFold might do for drug discovery, but even if scientific improvements are made on that front, there's never going to be a pill to get rid of depression, stress, anxiety, or help you deal with relationships. BetterHelp is different from traditional counseling. The online model really changes the game. You can send a message to your counselor anytime. You'll get timely and thoughtful responses, and you can also schedule weekly video or phone sessions. BetterHelp's professional network of therapists that come from all 50 states, since you're not necessarily tied to a local counselor. BetterHelp gives you access to a wider portfolio of professional therapists to find someone who really meets your specific needs. I want you to start living a happier life today, and as a listener, you'll get 10% off your first month by visiting our sponsor at betterhelp.com/dataskeptic. BetterHelp, HELP.com/dataskeptic. So hard, you will find many websites calling it NP hard, meaning it's amongst the hardest problems that would have to be solved on a non-deterministic polynomial time machine. In truth, I think it's a distraction to talk about complexity theory here. I'm reminded of former guest Scott Aronson and his famous work as a brief experimentalist. All of this is covered, by the way, in his excellent paper, NP-Complete Problems in Physical Reality. It has been observed, and you can probably do this yourself, that if you play around with soap bubbles, they solve a sort of a minimization problem, or at least they seem to. By and large, when you set up different conditions under which bubbles might attach to certain things, be it 2 plates of glass connected with some nails or whatever, that they will find the lowest energy state, the sort of most efficient bubble they can form. And the flawed logic goes, well, if they find this minimization, and in the general case, finding minimizations like that is NP-complete, then it must be that soap solves NP-complete problems. Wash your hands, everybody. This is not only wrong, it's fractally wrong. As you zoom in, the wrongness is there all the way down. First off, the experimental results. As Aronson showed, sometimes the soap bubbles find inefficient solutions. Even besides that, it's not that impressive that on many occasions the soap bubbles could find a nice solution. I mean, if you live in a country where every city has a highway in and out leading to only one city and your whole country is just basically a ring of cities, then the traveling salesman problem is quite trivial to solve. But it's not the ring country we're concerned about. It's the set of all possible roads. AlphaFold 2 made the best prediction in 88 out of the 97 targets used in this competition. So our discussion related to complexity gets hung up there. This isn't a perfect algorithm. Maybe it's epsilon close to perfect or something like that. Even evaluating its complexity is a little tricky. Our input size is what? N, the length of the amino acid sequence? Knowing that this solution ran for a couple of weeks, I believe, to find their initial model, well, I guess maybe we're dealing with some n to the very large p polynomial time algorithm. I'm not sure, and I'm not sure it matters too much. Maybe their algorithm does take exponential time, but we're fortunate that these sequences are short. Regardless, it runs in a practical scale amount of time. If I'm understanding correctly, the proper use of AlphaFold could speed up research by at least an order of magnitude. Sometimes measuring these things empirically could take up to a year. If AlphaFold does it in 2 weeks, then that number's only going to go down. This is quite a leap forward. I'm not going to call it a quantum leap, primarily because I'm aware that a quantum leap is actually the smallest distance you can go, so it doesn't really hold up with the popular use of that phrase. But my takeaway is that this protein folding problem was difficult on a number of levels. It's just sheer raw difficulty, first and foremost. Second difficulty, the degree of expertise you'd have to achieve in biology just to get the basics. I mean, I looked at some of this stuff and I did some folding at home back in the day, and I might as well have been trying to read ancient Greek. I'm not saying I have some sort of cognitive blocker where I couldn't understand it, simply that's going to take weeks, maybe years of study. Perhaps to trained eyes some of the features are obvious, but not to mine. But if I re-engage my little fantasy about shrinking myself down and seeing what's going on with the folding, if I were to witness a sequence of amino acids folding up, I don't think it would be like a game of chess where the various pieces are strategizing against each other. I think it'd be more like dropping a wine glass. As it falls to the floor, I know the formula to calculate its displacement. That's basic Newtonian mechanics. What's a lot harder is when that glass hits the floor and shatters into a million pieces. Those pieces are just obeying the basic laws of physics, blissfully unaware that they're spreading themselves out into an incredibly complex and hard-to-predict pattern. But it is a pattern that emerged from basic and fundamental laws. What is rather impressive, though, to me personally, and maybe this is a first, I can't quite think of anything else that does this, is it seems AlphaFold developed a solution that human beings hadn't. We've had all this same data. We have very good computing devices in our skulls. Yet to the best of my knowledge, there was no protein fold whisperer. No person who could go into a trance and intuit the exact folding that a sequence would do. I've seen some pretty impressive feats of intuition by people who have gone deep into one area of expertise. It doesn't seem that any human being trained their eyes to look at that amino acid sequence and learn how it would fold. Memorize how known sequences would fold, that's not a problem. In fact, it was a bit of a problem for the CASP-14 team. I don't know how seriously this was entertained, but from what I understand, there was some concern that perhaps the performance of AlphaFold was due to them having secret information of some kind. The sequences used in this competition were meant to be previously unknown. This is effectively the holdout set. How do we test that these algorithms haven't just memorized the known already solved configurations? Just like a chess program has memorized certain endgames. Certainly some of that goes on, and that's fair. These things must fold in analogous ways. But probably the reason why this competition happens only every 2 years is they need enough challenger sequences. So I suppose labs that can contribute things they've synthesized recently and kept private as ways of testing these algorithms. The need for these novel examples to test is actually how people have explained variants of this project over time. If you look at the first place winners from 1994 up to the most recent 14th run, you actually see some years of decline. There wasn't a monotonically increasing sequence. Why not? Because some of those challengers were easy to solve. There's a variance there year to year. But with the 2 previous years of AlphaFold's performance, it seems pretty clear. Even if for some reason there were especially easy sequences presented as challenger sequences, this is still a major breakthrough. But congratulations to the team, the field, and maybe to all of us humans as a species. This seems to be a monumentous occasion, one whose impacts might not be felt overnight, but certainly an impact that future generations will just take for granted. Throughout all of DeepMind's achievements, the common thread is heavy compute, algorithms, and data. I look forward to seeing what comes next, including next week's show when we go back to our typical interview format. But for now, that concludes this installment of Data Skeptic Consensus. Our theme song is Paradox by Odling. Claudia Armbruster is our associate producer. Vanessa Burciaga does guest coordination. In resuming lockdown here in Los Angeles, I've been your host, Kyle Polich.